Hello, this is our final project for cardiovascular engineering, and we're gonna start. Okay, so as an introduction, in the past, many proposed aneurysm models have been neglected due to the fact that when in vivo imaging data is recorded or taken, the tissue is already submitted to a lot of stress conditions regarding blood flow and regarding also the normal characteristics and properties of an artery inside the body. So when external loads are applied, the results are over-elongated artery sections, unrealistic physical deformations, and large strains, according to Guy 2009. Another factor is that very little research has been done regarding unruptured aneurysms and the evaluation of the shape of the lesions, despite clinical evidence that the lesion shape is an important parameter to evaluate wall tension and rupture. George Gerns in 2008. So what this provides for us is the base for the next project. The implementation of a CFD or computer fluid dynamics aneurysm simulation with specific boundary conditions and lesion shape variations. The motivation behind this project is very similar to the introduction quotes. As the research in the literature review revealed, very often CFD models are created considering the geometrical data acquisition as pressure equals zero, while in the real world it is not that way. So it often leads to incorrect interpretation and false stress and displacement output data that can affect the patient or even the diagnostics. As part of our methodology, we designed the method to achieve the in vivo pressure conditions. We designed a pressure correction parameter in which we removed the base pressure of the artery by applying an offset pressure on the walls of the aortic lumen, therefore emulating an in vivo representation without fluid of the aortic aneurysm. Here we can see the boundary conditions for the study, and we can clearly see the fixed points marked in orange right here as a no displacement area, and it is basically just applied on the cylindrical faces of the aorta. After that, we have applied the artery material properties. We can see an elastic modulus of 1.48 megapascals and also a yield strength of 1.44 megapascals. The pressure correction parameter was set at 100 milligrams of mercury. It is the mean pressure of the aorta at all moments. To actually create the pressure correction parameter, we had to create the finite element design first on SolidWorks, where we actually managed to export this geometry to nTopology, which is the software you are now seeing on your screen. The first step was importing the mesh, and this is the mesh you actually get of the deformed aneurysm, and you can clearly see that there are a lot of irregular mesh parts that will not be able to provide any processing unit for the computer fluid dynamics analysis. So what we had to do was remesh it in order to provide us with a more clear, and here you can see a more symmetrical mesh that provides us with the faces enough to provide the pressure correction, which here you can see the faces in which the pressure is going to be applied. After that, we actually set the boundaries, so you can clearly see here. Sorry, let me just. Okay, so after that we managed to apply the boundary conditions. Here the fixed points on the top and of the bottom of the aneurysm. After that we created the pressure vectors or direction applied on the faces, and then we set the isotropic material properties, which are the same you actually reviewed on the last portion of the video, and we managed to provide the analysis results, which is the deformed version of the aneurysm, which provides us with the zero pressure correction. After the finite element pressure correction, the inverse design has left us with the aneurysm model that provides us with the trustworthy parameters and boundary conditions to provide computer fluid dynamics simulation. So here you can see on the left right now, the one that I'm signaling with the mouse is the thoracoabdominal fusiform aneurysm before the pressure correction, and then on the right it is the same type of lesion but with the pressure correction parameter. So we can clearly see a more relaxed and stress-free configuration of the aneurysm that is now available due to the pressure correction parameter that we set on the finite element simulation. Now we can also see here in the bottom the saccular infrarenal aneurysm before the pressure correction and after the pressure correction. Now we can provide an accurate CFD simulation with trustworthy results that doesn't ignore the parameter of the zero pressure and actually takes it into account and provides us with the base point and the starting point for actually a precise and accurate design.
In order to proceed with a particular analysis on a specific activity that our patient needs to deal on a daily basis, we will have to simulate starting with the zero pressure geometry. So let's suppose our patient is playing with his son or giving him a hug, and he experienced a little bit more pressure in his abdominal cavity than he would normally do. Pressure rises up to 120 mercury millimeters, and this will change the geometry of the aortic wall. So in order to account for this, we will perform a simulation on this geometry to see how the geometry changes during this event. Using the correct material properties, we'll get a more precise geometry for this specific case. Then we can compute fluid dynamics and fluid simulation, finite element techniques to see how this will change the flow of blood in this region. Now that we are in the flow simulation model, we will proceed to build a transient flow analysis. Proper blood fluid properties, our model is complete. We will proceed to define the inlet velocity or average velocity. Since blood flow is not constant, non-zero at any point, a Gaussian bell curve approach was taken in order to simulate as close as possible the pulse nature of the blood flow in the aorta. After fulfilling those inlet velocity initial conditions and the pressure at the end of the aortic branches, we are ready to start the simulation and wait for the correspondent results to pop up. So the main plots we're showing will be relative to vorticity, velocity, pressure, shear stress, all of them published parameters that are of great importance to determine if an aneurysm will end up in disaster or internal bleeding. The results will be shown next by my partner.
Contrary to what Suzuki said, the regions with the higher wall shear stress were the ones that had the aneurysm, and it also had a higher velocity. The aneurysm model in this particular study had an outlet velocity of 4.3 meters per second, being one of the highest velocities throughout the study, and having a direct relationship with the wall shear stress. That is also the highest at nearly the same point of the artery, having a value of 109 pascals. This can state that nearby at the final point of the aneurysm, the rupture is the most probable, because it has a high velocity and a high wall shear stress. So, in summary, our results deliver different information than the one that has stated by Suzuki in 2009. While having an extra pressure of 20 millimeters of mercury in this model, the wall shear stress and the velocity are remarkable in the final part of the aneurysm, suggesting a rupture point in that exact point or nearby the bifurcation. In order to give a clinical application to the proposal that we have made, it is proposed a computational fluid dynamics risk assessment for the aneurysm rupture point that will be explained by my fellow teammate.
To give a clinical application to the proposal made, is propose a computational fluid dynamics risk assessment for aneurysm rupture. This assessment ends with a proposed indicator, the PIT. that quantifies the risk of rupture, taking into account various risk factors, such as large aneurysm diameter, a rapid expansion rate, smoking, female sex, hypertension, a history of cardiac or renal transplant, decreased forced respiratory volume, and lowered wall shear stress. This is the clinical protocol to be followed for the computation of fluid dynamics risk assessment for aneurysm rupture, and this is a precise formula for calculating the proposed indicator. The fixed values that are used for the parametric aneurysm threshold calculation were obtained from the literature on aneurysm rupture risk factors. This PIT indicator is a symbol for the MDRD for estimation of glomerular filtration. It is neither supposed to substitute medical imaging techniques for diagnosis nor to substitute medical evaluation of the cardiologist. Instead, it is supposed to be a useful indicator that provides a numerical backup to the cardiologist's evaluation of the patient's situation, just as a nephrologist uses the MDRD.